In this video, we examine the detailed mechanism of a transesterification reaction taking place under basic conditions. Okay, so the overall reaction for transesterification, as I introduced to you in the previous video, is you have one ester becoming another. So in this case, we have a methyl ester becoming an ethyl ester. The reagent that we're using for this is sodium ethoxide. The solvent that we're using for this is ethanol, which is of course the conjugate acid of sodium ethoxide. Ethanol is under some conditions capable of being a nucleophile, but as we're going to see in this case, it's not a good enough nucleophile, but sodium ethoxide is a good enough nucleophile. So this is a fairly straightforward mechanism. It is a simple two-step mechanism, addition followed by elimination. Okay, so in the first step, the ethoxide comes in, attacks the carbonyl carbon, needs two arrows, one to form the bond from the oxygen to the carbon, and then the other arrow to break the CO pi bond and put those electrons onto the oxygen. That leaves us with a tetrahedral intermediate that has a negative charge on the oxygen, and then that's going to want to kick out a leaving group to regenerate the carbonyl group and leave us with a new ester. So in this case, to get us to product, we have to kick out methoxide as the leaving group, which will leave us with the ethyl ester product. Okay, so since this reaction is taking place under basic conditions, the alkoxide is nucleophilic enough to react with the neutral ester. And now, what you should definitely be able to figure out is that this reaction is reversible. There is no reason why the products, an ethyl ester plus methoxide, will not just go back and give the reactants a methyl ester plus ethoxide. So the overall reaction is reversible, but even more specifically than that, from the tetrahedral intermediate, there is no fundamental reason why it won't kick out the ethoxide that was just added in to go back to starting materials rather than kick out methoxide to go to products. When you look at the product and the starting material, they are both esters, so there is no thermodynamic reason why one would be more favorable than the other. They are the same on the relative reactivity of acyl carboxylic acid derivative chart. So what we need to do is we need to drive this reaction using Le Chatelier's principle. So here's how this works. You use ethanol as the solvent. You have lots and lots and lots and lots of ethanol in there, 100 times, 1,000 times, what have you, compared to reactants. So what's going to actually happen is most of the methoxide that you kick off as a leaving group is going to deprotonate an ethanol molecule just because there are so many ethanol molecules around since it's the solvent to deprotonate. That deprotonated ethanol then makes ethoxide, which is one of the reagents. So this process thus uses up methoxide as the byproduct, reactant D, product D, so to speak, by generating more ethoxide, the nucleophile, reactant B. Okay, so that's what will drive this reaction to completion. There's the transesterification mechanism under basic conditions. In the next video now, we will look at it under acidic conditions.